Do you see my screen now?
Yes, I don't know if we should just take a quick break.
Okay, maybe a quick break. So okay, should we get started? Okay, so so far in this school, we have been basically discussing elastic transport theory. And with this lecture, I'm going to talk a bit about how to go beyond such descriptions, and more specifically into this software project we call Inelastica, which is a Python code to compute molecular vibrations, electron phonon couplings, and inelastic transport properties. And it's basically also a bit of a history talking about what we did long time ago when I was a PhD student with the maths, together with also Magnus Paulsen, and we developed this Python implementation that I will be describing today. A little bit of brief motivation is maybe not so necessary in this forum, but going almost 50 years back, it was proposed theoretically to build a molecular rectifier using molecules between metal electrodes. This famous paper by Aviam and Ratner. And significantly later, this was also pursued experimentally to try to address the transport properties of individual molecules. I have a little problem here with the animation. Excuse me. Let's try again. Here we go. Yeah. So in this early paper here, using self-assembled monolayers on a gold wire in this break junction geometry, it was attempted to make metallic contact to individual molecules. And these are some of the earliest report on this kind of break junction experiment to chemically anchored single molecule junctions. And I wanted to highlight here is a little bit the order of magnitude. We're talking about micro amps passing through individual molecules and voltages of several volts applied across this kind of nano junction. And we've seen this kind of sketch. We built theoretical models for single molecule junctions and envision some chemical potential applied to these metal contacts. But it also raised these kind of questions. What about energy dissipation? We have volts across, and where are electrons dissipating their energy? And eventually also when such large currents are passing through individual molecules or individual atoms, what about the junction stability? So on one hand, this was a motivation for us. Also, from a maybe different point of view, is about the characterization of nanojunctions. And in this early work by Jaklevik and Lampe, they reported in voltage spectroscopy of metal oxide metal tunnel junctions features that they could trace back to the specific molecules that they had embedded in the oxide film. A real step forward, I would say, is towards nanoscience was the invention of the scanning tunneling microscope. And besides making nice images of individual atoms and so on, this was also taken to the limit of vibrational spectroscopy at the single molecule level, pioneered by the group of Wilson Ho. And what we see in the data here is the IV characteristic voltage versus tunnel current. With the tip position over an acetylene molecule or by the side. And the REV characteristics are not directly revealing much. You see just these straight lines. But taking a careful look into the second derivatives, as was done up here, one start to see some small fingerprints that were traced back to molecular vibrations. Another example is the creation of monatomic wires, as Matt's also mentioned before, using the tip of an STM, basically crashing it into the surface and retracting the tip. One can form this kind of metallic wires of a few atoms long. And here it was also experimentally reported how the conductance is changing when you apply a voltage of characteristic vibrations of this nano chain. And also another interesting report back around year 2000 was the measurement of transport through a single hydrogen molecule between platinum electrodes using break junction techniques, where again, in the second derivative of the current, one observed characteristic fingerprints related to the vibrational degrees of freedom of the single molecule. So as I said, for us, around shortly after these works were these inspirations to, at one hand, discuss stability and joule heating, and another one on this ITS strategy to really learn about the details of our nanojunctions and use it as a characterization tool. So the Inelastica project is a Python code that we have now in GitHub. And it's basically a little bit of a vintage code, I would say. It was developed before SIESTA that we are using these days, and before the many developments in the SIESTA code with the 4.1 series. So some of the tools we have here is a little bit of a duplicate, things that can now be done much more elegantly with SIESTA, but it's somehow a pending effort to try to upgrade these tools to more modern strategies. So going back to this ITS, to give you a better picture for the mechanism, imagine that we have here a small molecule on a metal surface contacted with the sharp tip of an STM. And when we apply a bias voltage, we can imagine now at low temperatures, we have incoming states from the tip side. And in order to have a phonon emission process in a Fermi-Goldin rule picture, we need an empty final state. So this is something that can only happen when the voltage exceeds the characteristic energy of a single phonon, h bar omega here. So this is what leads to a threshold behavior, as we can see here in the current versus voltage. What happens is that when the bias voltage comes across a characteristic phonon, there might be some correction to it. And this small kink might be difficult to see directly in the current because it's a small effect. It might be more clear in the first or second derivative of the current as indicated here. This kind of correction can be an increase in the conductance as we see here, or it can also be the other way around where the actual scattering starts to reduce the current flowing through our device. And some of these features can be rationalized in terms of a transport through a single molecule, where I'm indicating some relevant energy scales here. The phonon energy, the electron-phonon coupling strength. Gamma is the effective broadening of our level, and then the bias voltage here. And then also separation of the current carrying molecular orbital from the bias window. And we can basically distinguish between three different regimes: off resonance, when this carrying resonance is far away compared to the other energy scales, or on resonance if this one, for instance, is in the bias window, or vibronic regime where the coupling and the lifetime broadening of the state is very weak. And this is typically not the things we are able to address with the techniques of SIESTA. So basically what we have in mind is basically these kind of situations where we have a good coupling to the molecule, but this resonance could be either off or on resonance. And we aim for a general description of such behaviors. We've seen this already several times in the SIESTA setup. We are partitioning the system into blocks due to the formulation in this orbital basis. And we can compute transmission functions and currents following this formula here. But how do we go beyond that? If now, say, we have a vibration going on here and an inelastic scattering process taking place in our device, we cannot apply this theory as it's written here. People figured out using non-equilibrium Green's functions how to address it in a more general framework. And this is a celebrated formula by Mir and Wingren. In this form, I'm writing it here. We can express the current flowing out of a certain electrode labeled alpha here as this kind of a detailed balance equation where the Green's functions are now not the retarded Green's function we have heard about these days, but this lesser and greater variant of it, basically representing the greater part for the empty states in our device and how they are being filled by electrons coming in from electrode alpha. But from that, we also have to subtract the outgoing, namely the filled states of our device and how they go out into electrode alpha. And this is a strict derivation that holds also when we have different interactions going on inside our device region. So we can use the Dyson and Keldy's equations to express the device Green's function, taking into account various types of interactions. And specifically here, we would have the electron-phonon interaction coming into play here as a self-energy. And also so now the more complicated part is that now it's not just a single Green's function. We have at least to work with two in this steady state regime. So we also express equations for the lesser and greater part. And the phonon self-energies take this form here in the approximation where we just consider the lowest order Feynman diagrams to the self-energy. It will involve electron-phonon coupling matrix elements, electron Green's function, and phonon Green's functions. Now, in principle, this could then be addressed also from an ab initio point of view. The complication here is, at one hand, we need a self-consistent scheme. As you see here, the Green's functions depend on self-energies, but the self-energies depend on Green's functions. So in order to solve this self-consistently, it would be necessary to iterate. And the boldface notation indicates our electronic space, which is typically huge for ab initio descriptions. And there's also this additional complication of the energy integration, that things are convoluted in energy, that the self-energy at one energy couples to Green's functions at different energies with the phonon energy. So in order to really make this feasible for ab initio simulations, we did the following of considering just effects to second order in the coupling M, as well as to make this approximation that the vibrational frequencies energies are typically small compared to the variations in the electronic structure. So what about evaluating all the electronic structure properties at the Fermi energy? So in this case here, we would simplify the equations by saying the Green's function is approximately the value we find at the Fermi energy, gammas at the Fermi energy, and spectral functions, and so on. Then we can come back to the Mir-Wingren formula and make this expansion to second order in M. And the attractive part is that the expression can be separated into some electronic structure terms, these traces that you see in this horribly long expression, multiplied by some functions that take into account the voltage dependence. Basically, the functions that is shown here in the second derivative, something that is like a step function that leads to a peak or dip in the second derivative, and some asymmetric term that kind of skews the shape, line shape around the threshold energy. It's also possible to go a little bit beyond this, keeping the idea of second order in the coupling, but allowing for some variation over the energy scale of the phonon energy. And we found some years ago a little bit more general expression for these conductance, the trace part. The universal functions were the same, but how to get the amplitudes of those functions from each mode lambda, taking into account finite energy of the phonon. And as a note, because later today you'd have the exercise of using Inelastica, this kind of expressions are the default, but it's up to the user if one wants to return to our initial formulations. One can play around with this parameter lowest order scale that sets whether this finite phonon energy is being fully taken into account. If this value is 0, we'd go back to evaluating everything at the Fermi energy. One slide about how we compute the electron-phonon couplings in Inelastica. This is based on a finite difference scheme. So we typically have this kind of setup that we have our device region coupled to semi-infinite electrodes, and some subset of the atoms inside the device are allowed to vibrate. So we are also thinking about localized vibration. The way this is then computed is that using SIESTA or trans-SIESTA mode, we move atoms in the Cartesian coordinates and save information about how the Hamiltonian changes and how the forces change. And this allows us to compute in a finite difference scheme not only the dynamical matrix, but also how the Kohn-Sham Hamiltonian changes along these normal coordinates. And a little technicality by working in atom orbital basis is that when we displace an atom, we not only perturb the system, but we're also expressing the Kohn-Sham Hamiltonian in a different basis, the shifted one. And this leads to these pulley type corrections where we need to know a bit about how is our overlap matrix changing when we move atoms. And this is a special run that one needs to carry out for doing these simulations. A little bit of an overview of the workflow within Inelastica. It's a set of scripts that you can run from your terminal. And the workflow is as follows. Typically, one starts with obtaining the junction geometry using standard relaxation. And on the one hand, one can then use this as for set up the trans-SIESTA calculation with the coupling to the semi-infinite electrodes. In a parallel effort, we need to compute the vibrations and electron-phonon couplings. And this is then combined at the end of the day using the script that is called Inelastic. So it's both the name of the package and the script that gives us the final output of this workflow. The package also offers other scripts, like there's a geometry utility that can convert between different formats. And PyTBT was an effort to basically implemented TB-trans type of calculations in Python, but that's a long time ago, and now everything is much better available in CISL. And there's this script that Matt's talked about, eigenchannels to really write to compute the eigenchannels and the scattering wave functions to a file that you can visualize. Over here, we have some scripts to help the user setting up the finite displacement runs, and this one to explore the change of basis when atoms move, which is then after finishing this set of calculations, one can compute the phonons and couplings with the phonon scripts. And again, these things are then combined at the end of the day in an Inelastica call, and you will learn about this in the tutorial. A few examples. I would say that it has been applied for many types of organic molecules between metal electrodes. And here I show you an example where high quality experiments are compared with the output of an ab initio simulation for a specific alkane thiol molecule between gold electrodes. And the quantity that is shown here as units. So it's a direct comparison of the second derivative normalized to the first. And this is conventionally what we call the ITS signal. And as what you can see here, not only can we make a link between peaks related to specific modes of the molecule, but also absolutely the magnitude of the signal is relatively accurate, or say at least within an order of magnitude reproduced by the simulation. As I said in the beginning, we were also very much motivated by these experiments of characterizing atomic chains. And the curves you see here present both experiment and a theoretical simulation. And little noisy black curves here are different conductance measurements as a function of bias voltage at different strains of the wire. And the main, this is the second derivative of the current down here. Now we see that the conductance is being reduced as we sweep the voltage. So here, the effect of phonons is to backscatter electrons. And in principle, this kind of wire of a few atoms would have many vibrational modes, but if one looks at these curves here, it's basically like there's a main feature related to a phonon of the 10, 12 millivolts. I think Matt's also had this in his slide, but if we think of the infinite gold chain, it's basically this half-filled cosine band. And when we apply a voltage, we'll start to populate slightly more the forward-moving states than the backward-moving states. And at low temperatures, an emission process would lower the electron energy, and it can only find available states here at the other side of the band. So it gives us kind of a selection rule for which modes that can scatter electrons, namely those where the phonon wave vector meets a change of the electron by 2 times kf. So it's the zone boundary phonon, longitudinal zone boundary phonon that can bring us from here to here at low temperatures. So it's a simple argument why there's one characteristic mode that is the active one for the gold wire. Another aspect I wanted to highlight at this stage is the fact that beyond the onset of phonon emission, we tend to see some slope, that the conductance is not just a step here, but it really has decreases further as we ramp up the voltage. And this is something we can also describe in the model by developing a rate equation for the effective mode occupation as written here. So there's some power that is being transferred to the phonon from the coupling to the electronic current. And then there's a damping term that brings us towards the Bose-Einstein distribution. Now, if these wires sustain enormous microamp currents, so there can be different effects here. First of all, there are different parameters for this damping here. And two extremes would be that there's no damping, or there's a maximum damping where every time an electron enters the chain, you again see the thermal distribution of modes. So it sets kind of a window here, and we can even try to extract from the slope here what would be the effective damping of such a phonon in the wire to its environment outside. So this is the effect of heating, how the vibrational mode is being heated up as the voltage increases. As a last example, and this brings us towards the tutorial today, is the vibrational spectroscopy of a CO molecule on a copper surface. And there was a very nice paper years back on not only CO characterization, but also CO manipulation on surfaces. And here you see it in the red dots indicated the position of individual CO molecules that could be manipulated with the tip of an STM. And this paper addresses many interesting aspects of building kind of molecular cascades with CO molecules. Here I want to highlight an aspect where they use ATS on this molecule. And what is seen is that voltage range up to 40, 50 millivolts are 2 peaks. And those 2 peaks can be understood in terms of the vibrational modes of CO, namely frustrated translation and frustrated rotation modes of the molecule. Now you see they're both a red and a blue curve here, and this corresponds to different isotopes of the molecule. And due to the different masses, the vibrations are going to change a little bit, and this is indeed what is being observed, that the lighter molecule has a slightly higher energy, for instance, for this frustrated rotation mode. So in the conductance curve, we have this step here associated with the peak here. And now positioning our bias voltage at 35 millivolts, the conductance is going to be higher when we are over the isotope with the heavier carbon than over the carbon-12. And it allowed them to make this kind of sorting of individual molecules on the surface and to write carbon-12 and carbon-13 by the vibrational effect. And later we also had we also studied this problem with the experimental colleagues in San Sebastian, who not only characterized the molecule with the tip in the tunneling regime, but also approaching the tip to bring it into contact with the molecule. And this frustrated rotation mode around the 35 millivolts was found to undergo a shift when it started to be in contact, chemical contact with the tip. So here my colleague Gatfield might be around this afternoon. She carried out extensive calculations using Inelastica to compute the vibrational modes as a function of the electrode separation and how that affected the corresponding IETS. So on a general level, we could reproduce this kind of effect that when a new bond or contact to the tip is formed, this frustrated rotation mode undergoes a shift in good agreement with the experimental data. To understand a bit better what is the origin of the active modes and the so-called propensity rules, it's very helpful to look at the elastic eigenchannels as Matt's introduced in the lecture before me, because you can think of it as a basis change where we only have to consider scattering rates between these eigenchannel states. So for the CO molecule between contacted with a metal tip, this problem can basically be understood in terms of three active eigenchannels. Two of them with a pi-type character that is traced back to the molecular resonance, the 2-pi star resonance of the CO molecule, plus something that is more of rotational symmetric from the S-wave tip side. So what you see here, we have three channels, but we can in each of these channels send an electron wave from either left or right side. And if we ask ourselves for transverse modes like this is the frustrated rotation mode, how can this scatter between these electronic states? So the kind of deformation potential this mode was set up with the transverse motion would be like an odd deformation potential. So what I'm trying to sketch here is we're looking at this kind of Fermi-Golden rule rate, bringing us from one scattering state into another, mediated by a phonon coupling matrix element. And if we have this transverse mode, we cannot obtain a totally symmetric product if we start from an S wave and want to leave in this S or sigma eigenchannel. Now, what we need is, for instance, an incoming S wave scattering against this odd function and into one of the pi, and vice versa. You can start in a pi state and scatter into a sigma. So it's possible to get these rates expressed with Inelastica in between the eigenchannel scattering states. So for instance, in this specific problem here, the problem is boiled down into a 3x3 matrix of rates. And it's being identified numerically that the scattering process that dominates this problem is a scattering from an S wave initial state into the pi states of the on the CO molecule side. So this kind of eigenchannel analysis helps us to understand which are the underlying electronic transitions that can occur due to symmetries in the problem. So by changing the symmetry on the tip side, one can put different molecules on the tip side and then explore the interplay between the orbital symmetries and the intensities of the inelastic signal. So for instance, if the tip is replaced by a CO molecule or this C2H4, one can suppress dramatically the signal from this frustrated rotation mode because we have effectively suppressed the S-wave character from the tip side by having the extension on a pi-type molecule. So this brings me to the tutorial we prepared for you today. It's a simple representation of this problem of a CO molecule on one-dimensional chains. It has a number of limitations that you will see because there's not the same electronic structure to put a molecule in this chain geometry as on an extended surface. Nevertheless, it will allow you to play around with the physics that I tried to explain today. So with this, I would just like to acknowledge many people that have been involved over the years, in particular Mats and Magnus, with whom we worked hard on this problem and coding things up. And I thank you for your attention. So I'm happy to take some questions. Asa asks, is it possible to do phonon calculations for many electrode systems using Inelastica? This is an excellent question. It's not possible with the version we have at GitHub at the moment, but we are working on extending this to based on a SIESTA implementation to make it compatible with the new SIESTA. And I know Jonas, who's also here in the audience, he's been coding up things in this direction. How about the homo-lumo gap affect the validity of this approach in case you have molecular vibrational states? So general rules, I think this is what you're asking for. When the homo-lumo gap is large, you can still have the excitation of the vibrational modes, but then we are working in the off-resonant regime, and the effect of a phonon is basically to help you tunnel through the molecule, and you'd see increases in the conductance. So general rules is a little bit this about whether we are on or off resonance, whether the conductance signal is positive or negative. Enrique Morium is asking, is it possible to have relaxation time with this methodology? Wonder about which relaxation time you're referring to, the phonon relaxation time, or because or the electronic relaxation time, because we are not really able to handle bulk problems with this method. As I explained, the outset from this development was localized vibrations in some kind of nanostructure. Able to account for optical and acoustic phonon scattering separately. Okay, so maybe this was not so clearly expressed. We have a finite number of modes, basically the dynamical region for each vibrational atom. We have 3 degrees of freedom, so we get 3 times n vibrational modes. And so we have everything resolved mode by mode. It's also possible to use Inelastica to compute phonon band structures and couplings in in-box systems, but not in terms of inelastic transport, like Boltzmann transport equations, for instance. I see no further questions. A little bit, a few words on the tutorials. We have prepared 2 tutorials for Inelastica. The first one was what I was sketching here, going through the workflow of doing an IV calculation using Inelastica for a CO molecule between one-dimensional chains. The second tutorial is about eigenchannels, as Mads described, and as an example, he's using the electronic structure that you obtain in the first exercise. So you need to take them in this order, do the first tutorial before the second. There's a question now about MPI. No, it's not parallelized. Sorry. So the code is probably not, the interesting part from the coding side would be to really bring it in line with all the tools available in SIESTA. Yeah, Jonas, he's making aware of regarding the parallelization that it is parallelized in terms of OMP if you have proper installation of your NumPy library, because Inelastica is based on NumPy. So in that sense, yeah, there's a parallelization option. but it's not coded into Inelastica. Thank you all for your attention.